Welcome back. In this session, we'll continue with the discussion on realization of discrete time systems. Right? So we know the transfer function of a discrete time system, h of z, which is given as output transform divided by input transform, is given by something like this: k running from 0 to m, vk at 0 raised power minus k divided by 1 plus summation k running from 1 to n a k 0 from minus k. Alright, so this is the transfer function, general transfer function of an nth order system. Right now, in the previous session, we first wrote the zeros and then polars. In this session, what we'll do, we'll first write the polars, then zeros. Let's see what will happen to this. So first, we'll write this part. Then we'll write this part. Right. So let's call it as HPZ, means all polars of this transfer function, and then HZ of Z. HZ of Z means zeros of the, where HP of Z again is 1 by 1 plus summation k running from 1 to n akz minus k, and HZ of Z is summation k running from 0 to n dk 0 minus k. Right? So if we draw the structure of the system, we'll say y of z is equal to hp of z, hz of z, and then the input. Right? So how do we write this? As a structure, how do we write this? Or in block form, how do we write this? So there are two systems in cascade which are connected, and the input to the first system is x of z. And then first we realize these poles, then we realize h of z, and we say this is the total output is y of z. Let's again represent the intermediate output as wz. So wz is our output, which is given as x of z, hp of z. Now substituting, what will be y of z? Y of z will be simply input here is wz, then multiplied by the transfer function of the block. So the transfer function is z of z. Then substituting wz here, we'll get hp of z, hz of z, xz of z. Isn't the same? So this is that. So what we'll do, first we'll try to realize this, then alright. So let me write wz first. So we say wz is equal to hp of z multiplied by x of z. Right? So what's hp of z? hp of z is 1 by 1 plus summation k running from 1 to n a raised power k, z raised power minus k, x of z. Now rearranging the terms, we can write x of z as, write it like this. So we can write x of z as 1 plus summation k running from 1 to n a k 0 is from minus k, and w. And shifting this term on the right hand side, we are multiplying with wz, can write w3, and summation k running from 1 to n a k 0 is from minus k. So this will be wz plus wz summation. Now expanding this will be a raised power 0 is power minus 1, a2 0 is power minus 2 plus so on up to an 0 is power minus. Now multiplying each term with wz, we will get a1 0 is power minus 1 wz, right, plus a2 0 is power minus 2 wz, plus so on an 0 is power minus 1 w. Right? So this is our x of z. Now taking the inverse z transform on both sides, what we'll have x of n is equal to wn plus a1 wn minus 1, right? The z transform, inverse z transform, this will be wn minus 1 plus a2 wn minus 2 plus 1 an wn minus 2. Right? So this is our expression 1. So this is our first expression. So this is the expression that we'll use to realize the poles. So this is the expression that we'll use to realize the poles of the system. Right? So this is our expression 1. Right? Now to realize the second equation, the second part we said yz. So we said yz is equal to wz multiplied by hz of z. Right? Now hz of z is, what's hz of z? Substituting that here. This is summation k running from 0 to n, sorry, m, not n, m bk 0 from minus k, and expanding this summation, we will write it as wz b0 0 is equal 0, b1 0 is equal minus 1, b2 0 is equal minus 2, plus so on, bm 0 is equal minus 1. Right? So y of z will be equal to wz b0, this is 0 is equal 0 is 1, b1 0 is equal minus 1, wz plus b2 0 is equal minus 2, wz plus so on, bm 0 is equal minus m, w. Right? Now again taking the inverse z transform, we'll have y of m is equal to b0 wn plus b1 inverse z transform of this is x of n minus 1, inverse z transform of this is b2 x of n minus 2 plus so on, bm z is x of n minus 2. Please have a look at this. So this is the inverse z transform of the second part, the second block. Right? So this is the inverse z transform of the second block. Right? So this is the inverse z transform of the second block, and we'll realize this part as well. Right? So what's our first equation? Our first equation is this, and our second equation is, sorry, this is Wn. I have written it wrong. This is not x of n. This is Wn. Sorry, this is Wn. This is Wn, not so we are realizing the Wn. Right? So let me write these two equations in the concise form. So x of m is equal to Wn, I think. Then this term, these terms are write as summation. Summation k running off from 1 to n, a k w n minus 2. And the second equation is y of n is summation k running from 0 to m bk x of n minus 2. So these are our two equations that we need to realize our discrete time system. Right? So these are our two equations. Right? Now what we'll do, what our input to the system is x of n, right? So our input to the system is x of n, and our output to the system is this y of n, right? Y of n. All right. So how do we realize this structure? That is the question. So how do we realize this structure? First we'll do this part, then we'll do this part. All right. We'll do first this part, and then we'll do the second part. All right. First, let's do this. Let's do the first equation. So how do we do this first equation? All right. How do we do this first equation? How do we write the first equation? All right. So to realize this expression, what we'll do, we'll say Wn is equal to x of n minus Q from 1 to n ak w minus k. Alright, I can write it like this: x of n plus summation Q1 from minus 1 to n, and I will write this ak like this. Alright, so let me realize this expression first. Alright, so what I have x of n, and then I'm adding these terms, right? So first let me get this. Let me get this one. So this will be Wn minus 1, Wn minus 2, Wn minus 3, and each term is multiplied by a1, a2, and a3. So suppose I have here Wn. So this is our Wn. So this is our Wn. How do I obtain Wn minus 1 from this? So what we do, if you remember, we simply delete. This will be Wn minus 2. Sorry, Wn minus 1. Then we again delete, and this will give us 1. This will again give us Wn minus 2, and so on. To continue this, finally what we have, this will give us n minus m. So this is the mth delay element. So this is Wn minus m. So this will be Wn. Alright, then what we'll do, we'll pass these through multipliers. Alright, so we'll pass these through multipliers, and the multiplier coefficient is here minus a1 minus a2. Why minus 1 minus a1 minus a2? Because of this term. Minus a1 minus a2, so on up to minus am minus 1, and this will be simply minus a, right? Sorry, an. I think it's n. Yes, nth term, not m. This is m. So this is m. Everything counts. So this is m. This is again m. So this is n. So this will be n, and this will be n minus 1. So the output will here be, what will be these outputs? So this will be minus a1 w1 minus 1 minus a2 w minus 2. This will be minus a n minus 1 w n minus n minus 1. Please pay attention to the last term. This will be minus a n w n minus capital N. Alright, then what we are doing, we are simply adding these terms, summing these terms. So first you can add these one by one, or you can add these together. So you can do it like this. Adding this. Finally, you add these terms once we have obtained this. So this is the output, this term, this whole term is available here now. So what you will do, you will add to this x of n, and that is your Wn. That is your Wn here. So Wn is available here. All right. So Wn is available here. Alright, so Wn is available here. Now what we'll do, we'll try to realize the second expression. Now we have Wn available here. Alright, what we can do, we add these bk Wn minus k terms and realize y of n. That's our output. So the output is y of n And how do we obtain this? How do we obtain y of n? We first add these terms. So first let me realize this. What is this? First I will delay this. Then I will obtain w n minus 1. Then what we'll do? Again delete. We'll obtain w n minus 2. Then we'll again delete. We'll obtain w n minus 3, and so on, and so on. We'll finally have m. Now, depending upon whether m is greater or n is greater. So this will be inverse. This will be n minus m. Then we'll pass these through multipliers, right? And then we'll obtain the output slide. Sorry. So this will be like this. All right. So let me write the outputs. What is the output available here? So if I say this is Bm, so output will be Bm x of n minus n. So if this is B3, output will be x of, output will be simply B3 x of n minus 3. If this is B2, output will be B2 x of n minus 2. B1, the output will be B of x of n minus 1, and so on, right? So what we'll do next, we'll add these. So there we will have one output, we'll add it like this and this. Then we'll add this, so on with this. Then we'll add this to this, and we'll add this to this. This will give the term. Finally, we'll add the last term. Means there's Wn pass it to B naught. So the output will be B naught x of n, that is embedded in this expression. That is in this expression. Finally, we will obtain y of n, right? So this is our y of n. So what we have done in this, here we have all poles are realized on this side. Here we have all zeros. And this is referred as direct form second structure. This is referred as direct form second structure. Now, an important advantage of direct form second structure is you can remove half of the delay elements. How? Sorry, not half, you can remove some of the delay elements. How? Now, have a look at it. The same signal is available at this and this. So this gives you same signal. So you can eliminate one of the two. Either you eliminate this, because you can tap it here and connect it with this directly. You can remove this and tap it here. So you can remove some of the delay elements. So let me redraw the structure. Let me redraw the structure. First, let's redraw it. So now I have Wn available here. So what I will do, I will pass this through a delay element. Inverse. So here we have Wn minus 1. Then I will again pass this through a delay element. Then what we have Wn minus 2, and so on, and so on. Again, we'll pass this through a delay element, right? Then this will be W, let's assume this is Wn minus, I don't know which one is larger, M or N. So this will, this depends on that. Please pay attention. This depends on it. So this is Wn minus N, suppose, right? This is the, we assume N is larger, right? Then what we have to pass this through the multiplier. So here we have, so we'll pass this through multiplier. Suppose minus A1. Here we'll pass it through minus A2, and so on. Here we'll pass this through minus AN minus 1, and here we'll pass through minus AN, right? Now compare their signals. What will be output of these signals? Here we have minus A1, Wn minus 1, minus a2wn minus 2 minus an minus 1 wn minus n minus 1. This one is very, very important. So this will be minus an wn minus n. What are we doing? We are simply adding these terms now. Add this, and add this, and finally add this with this, and this will is added to x of n. And this, now we can tap it directly here and pass it through b1, sorry, not b0, b1. So this is b1, so this will be b1 wn minus 1 that we need in the second part, second equation, in realizing the second equation, right? And this is passed through b0, and this is passed through b2, and so on. And let's suppose this is bm, let's suppose this is our bm, right? So let's suppose this is our bm. So what we'll do, we'll add these, we'll add simply these, and then we'll add this with this. Please remember there is dash here, right? Then this will be our wire. Now see, there are only m n delay elements here. You can say there are only n delay elements. This is the advantage of direct form second structure. This is the advantage of direct form second structure. Now in the next session we will solve some examples so that this becomes clear, this procedure becomes clear. We'll solve some simple examples so that this procedure becomes clear. All right, let me end the session here.